equation estimate. Okay, so know the difference in your notation. Same thing with X bar versus X. X bar is the average of the X's. Just a single X is just we call it a realization. It's just a number. All right. All right. So we'll get started. Any questions on the admin part? We're all good. Now, this is called simple regression analysis, not because it's easy. It's actually not super easy. It's called simple because we have one explanatory variable that we talked about last week. When we get into chapter 15, we're going to have more than one. You can have as many as you like, but that's what simple means. So if we take the example with the real estate, we have houses. Let's say their market value. And we look at square feet. So let's say our explanatory variable in this case would be the square footage of a house. And then the response variable, or the Y, would be the price of the home, the market value. And we know that it would probably look like this. Right? Something like that, right? So as the square feet increase, larger home, larger price, higher price, right? And so what we do is we collect the data. We would have an explanatory variable that would be, it's usually on the horizontal axis, always on the horizontal axis, and its response variable is always on the vertical axis, okay? And if you're wondering when you're given two variables and you go, geez, which one should be which? Because sometimes it's not evident. What you want to do is you ask yourself the question, what are you most interested in knowing? So if you are most interested in knowing the cost of the house, that's your response. That's the output. Okay, so you're going to take, can the square footage predict the cost of the house? Okay, so what you're most interested in knowing here is the cost of the house, not the square footage, but the cost, right? So you want to always make it, the answer to your question should always be the response variable. So this is simple. In here, simple, specifically simple regression, because we have one explanatory variable. And that explanatory variable is also called the predictor. Predictor variable. It's going to predict, we're going to sub in square footage and hopefully get a good prediction of the house. Now, why would a real estate agent want to do this? Or why would a real estate company, the MLS and multiple listing services, why do they want to do this? This is so that, because there's so much variability, right? You could be a house on a corner, you could have a house with a swimming pool, you could have a double car garage, you could have single car. But if you take all that out and you're just looking at square footage, you're going to have a plot that has lots of variability on it because of all those other items, location and such. And then you get an average. And that average is going to be our Y hat equals our intercept that we estimate, which is B naught, and our slope. Right? Y hat. And why is it Y hat? It's so that we recognize, acknowledge that is the least squares regression line. It's the regression equation that we're going to use. Okay. So again, simple because it's one explanatory variable. I use it interchangeably. You'll hear me say predictor variable, explanatory variable, and so on. So when we get into chapter 15, we expand on everything and have more predictors, and we have what is called multiple linear regression. So that's the difference. There's either multiple linear regression or simple linear regression. As soon as you hear simple, just know that's the scatter plot. It's one predictor. Okay. Right, so the response, so somewhere in the universe, out there in the universe is the true equation. This is what we call the regression model. That is the perfect model if we had all available homes that were ever listed or will be listed, right? So it's like if we had the whole population, we would have the truth. And those are beta. So this is like the true values. No y hat, it's the truth. So beta naught, beta 1, so beta naught is our intercept, beta 1 is our slope, and then we have epsilon, which is our residual. And a residual is like the error, because we know there's going to be some error associated with all that variability. And then what we do is we estimate that using this line here. These are our estimates. They're not true. They're estimates. As soon as they're estimates, then we don't use betas. Our betas turn into B's, right? Beta, so beta naught estimates, B naught estimates beta naught, B1 estimates beta 1, and you have your X's. Those are your in square foot, if you will, right? And our Y hat would be our price. Okay, so that's the theory. And how do we get those values? What we want is we want to find the intercept and the slope. The intercept B naught and the slope B1, how do we get them? We have to come up with, we need the raw data, those pairs, right? All of these are XY pairs, right? XY, you have all these XY pairs on your scatter plot. We take all those XY pairs and we calculate the sum of the squares right here. There's some of them there. They're all right here though. So we get these sum of the squares with all the XY pairs. So we use the XY pairs, right? The original data, raw data. So let's say we have 100 homes, it would calculate it. We would probably by hand, we would do it. We would just get 5, right? To 10. And so this is what we do. So we get the sum of the squares for the pairs, X and Y, and you just multiply each one, and you can do it in pieces. I think you'll see in the textbook where they use tables, but it's actually, it looks like a lot, but it actually goes fairly at a decent pace. And you'll see the pattern with the sum of the squares for just the Y's, and then the sum of the squares for just the X's. So if in our case, if the X's are the square footage, you would just take each value of the square footage and square it and add them up. You would then take all of them and add them up and square the whole thing. So, because that's a little different, and then divide by n. You do the same thing with the Y's. It's done the same way. Take the Y's, the sum of, take each one and square it and just add them all up. And then you can add them all up and then square the sum total. Divide by n. Right, so each one of these are calculated from the data. And they're all calculator friendly. I find these actually faster to do than putting them all into tables, but I think you just find each little piece and then put them all together in the calculator. And back here, once we do that, we then estimate our Y hat. In this case, they're calling it the average. It's also, Y hat is actually the average. Mu they're using there in the textbook. So it takes all the data into consideration, and it finds the minimum distance for each of these vertical distances from the data to the line. Like it takes it minimizes the sum of all those vertical distances, and we call them Y minus Y hat. And each Y minus Y hat is a residual. And the sum of all those, the sum of all these equals 0 when we add them all up, because we've minimized them all. All those distances have to add up to 0, and you know you've done it right. And when you square them though, the sum of them all without the square is 0, but when you take them and you square them all, then you end up with, like, square each one, then you end up with what is called the sum of the squares for the error, SSE. Sum of the squares of the residuals. So you take each y, subtract the y hat, you're going to take them all and square them. Okay, and then here's how we get our slope. Our slope is B1. We get it first because the intercept needs the slope in its equation. So this is the formula for the slope coefficient, where I just showed you the sum of the squares of the xy pairs and the sum of the squares for the y. So actually that should be for the x's. I'm going to fix this. These should all be the x's. The denominator is the x's. Rise over run. I'll fix the slide. You can fix your slide. It should be the sum of the squares for the x's as given in the formula. And it's correct on the formula sheet too. Oh. If you see any error, let me know. Get a bonus point for finding these for me. Okay, so finding the intercept is a function of the average of all the y's. So we know how to get the average. That's just here. Right? These are the average, the means, x bar and y bar. So you take the average of all the y's from the raw data, subtract the coefficient that the slope coefficient you just calculated above, and then multiply it by the average of the x's. Right? That's all you need, those two numbers. If you have an intercept and you have a slope based on a bunch of data, the x's and the y's from the explanatory variable, you have your line. Okay. Sums of squares, 3 sums of squares right here. Okay. Let's try it. So this here data comes from a much larger data set, but I just took a random sample of 5 customers. So you know those online chat features where you can get help either by AI or by a person. Sometimes they'll, you know, it depends when you click on it, whether you might get a person or you might get AI. It's all sort of different timings of the day. So a company would be really interested in knowing if they should keep their chat feature because they're really expensive to have and run, right? So what you do is, well, I took this from a larger data set. I took 5 sales. So we have 5 customers. The time they spent on the little online chat feature for the company, and how much money they ultimately spent after they talked. Okay, so customer 1 spent 20 minutes. Maybe not talking the whole time, maybe like, you know how you have to wait for a response and then they find something, but all in all, it was 20 minutes and that customer spent $85. Customer 2 spent 55 minutes and spent $110. You can see the idea. We have our X. So which one would be, now you have the company, you're the data analyst, which one would be the explanatory variable and which one would you use for the response variable? So remember, there's that question, what are we most interested in knowing? Yes.
The response be the online sales and the explanatory be the time spent.
Perfect. Yeah, so this would be our why. We want to, that's what we're most interested in knowing. The company would want to know, is this chat feature worth the money? Okay, so this would be our X. We'll call it X and we'll call it Y because then we know which is which, and you can sketch that. We usually sketch this. So this will be our sales. And this will be our time. This is time spent. So we can do this. Usually we put like the average. So let's find the average time spent. That would be X bar, Y bar. So let's calculate these. You can get those. That's the first thing you usually do is calculate the averages for each of those variables. Then we get the sums of squares. We do a sketch too, because that ties in with the correlation. Because then we kind of want to see, is it linear? Because if it's not linear, we don't use these methods. Okay. If it's not, if the plot comes out looking like a star or something, or a quart or a, a cubic, then we can't use linear regression. Let me grab this. So does anyone have an average sales or an average time spent? Time spent. So that would be 20 plus 55 plus 105 plus 85 plus 45. 62 minutes. 62 minutes. And let's get the average sales as well. Anybody have the average sales? 40 cents? Okay, I'll just do 0.4, but it would be 40 cents. Yeah, 100. So the average sales, $107.40. 62. And what's our N? It's N is the number of pairs or number of customers in this case. So what do you N? 5, right? That's what you divided by. You took the sum of all those and then you divided by 5, right? Took the sum and divide by 5, yep. For 5 customers, there's our N right there. 5 customers. And we're going to fit a regression line, but I always like to do a quick sketch of this. So let's see if I can draw this. So our minimum is 20. So 20, and then this is starting at 85. So let's do something like that. So the first one, so I'm going to start here. This is starting at 20, 40, 60, 80, 100. Remember, a sketch doesn't have to look like software. It's just a sketch. So here we're going to have 20. This is going to start at 90. I'm going to start at 80, 90, 100. Move that over. 105, 110. And 120, 130. Okay, so let's try to get the points. Just look, without even drawing it though, we only have 5 points. Can anyone tell me what kind of an association we have here? What would, if you could guess, what would the correlation be? Just by looking at each pair. Right, because customer 1 spent 20 minutes. Yeah. Right, it's looking like with these 5, just by inspection, the more time spent on the chat, the more money was spent. So we're gonna have what kind of relationship is that between these two quants? Positive. Positive correlation, yeah. Let's see, positive. This is gonna be 20 and 85 would be about here. 55. That's going to be about here. Maybe here with 110. Okay, it's just a sketch. Not going to be perfect. The next one's 105 with 130. That's going to be way up here. And then 85, that would be about here. With 117, maybe here. And then 45 and 95 would be about here. something like that. Just 5 customers and we can see, and this was consistent with the full data set too. Positive association, positive correlation. Let's prove it mathematically. Do that. So what should we do next? What should we find out? Should get the sums of those squares, right? So let's do, which one do you want to do first? Which one should we do first? The X's, the Y's? We could just do one of them first. Let's do the X's first. Let's do this. Sum of the squares for the X's. SS stands for the sum of the squares for all the X's within, just looking at time spent. So the formula is the sum of the X's squared, subtract the sum of the X's all squared, divide by n. So there's half your marks. That's so important to know what formula to get from your formula sheet. Know the method, and then we just can get that subbed in. So we take all of the X's, so what you're gonna put here is it's going to be 20 squared added to 55 squared plus 105 squared. That's the first part. That's what X, the sum of all the X's squared. So you take each one and square them. And you should get that's what I get. And then you take the sum of them. The sum of all of them came to, well, if you know the average is 62, you can just multiply it by 5 to undo that, right? 62 times 5 gives us 310. That's the sum. 310 squared divided by 5 customers. And that should give us the sum of the squares. The first sum of the squares, right? So you'll see in the textbook, it goes through all these elaborate tables and the sums. It's just breaking all these components down. I find this less cluttered. If you just take each equation, plug it in, do each one at a time, and then just get your final answer. It's quite efficient. Does anyone have the sum of the squares for the X formula? Yes.
I got 12,400.
Perfect. That's what I get too. Yes. We put a box around it, keeps it straight. Let's do the same thing. You'll see it's exactly the same, but it's with the Y's this time. Same formula, but just use Y's. Again, write down your formula. Always, as simple and as trivial that may feel, just get your formula, and it will really help you make less mechanical errors as well. It also tells me in the marker, hey, I know I'm defending my decision here. So the sum, so you take each of those sales, so 85 squared plus 110 squared plus 130 squared plus 117 squared plus 95 squared, and you should get 589. See if you get the same as me. 39. Subtract. Now we have an average of 107.4. If you just multiply that by 5, it takes you back to the sum, which is going to be 537. Square it, don't forget to square it, divide by 5 customers. And we get that sum of squares. Anybody have a sum of squares? For the y's? You know what? 558,939, subtract 537 squared, divide by 5. What? Want to guess? Yeah,
I got 1,265.
yes, I do too. Okay, check and see if you do too. 1,265.2. I'll just keep 2 off. There we go. And finally, we do the combination. So that's going to be the sum of the x and y's. Each x and y pair is multiplied by each other, and then you subtract from it the sum of the x's multiplied by the sum of the y's. I'll divide by, you can guess, n. And that is going to give us. So what you do here to get the x times y, you go, first pair is 20 and 85. So you would take 20 multiplied by 85. Next pair, 55 times 110. Plus 105 times 130. Plus 85 times 117. Finally, plus 45 times 95. That gives us the first piece of that equation. $35,620. And you can verify that. The sum of the x's, we already know that from above. We know that that's 310. I put brackets here so I don't get all the numbers mixed up. The sum of the y's we already did above too, so we don't have to reinvent. You can just use those values from above. That was 537 without squares. There's our value. That's for the XY combination, sums of squares. And then we'll have all our sums of squares. From there, we find our slope, we find our intercept. We can get our correlation. Yes. Yeah,
Did you want to see two?
sure.
2,346.
Me too. Perfect. Thank you. 2,376. 26. Yeah, thank you. 26. Okay. Just looking at 2 screens, making sure. Anybody disagree? We're all good. We have our sums of squares from our raw data. That's from all this. This is the raw data right here. We call that raw data because it's just the XY pairs. Okay. So next we want to, first step I do after I get those is I get the slope. Because you need to know the slope to calculate the intercept. So the slope is V1 is equal to the sum of the squares of the XY divided by the sum of the squares of the X's. That's just a straight up formula. So we just sub those in. We've already done all the work. So it's going to be 2326 divided by the X's 4480. Yeah, make sure you grab the X's 4480. That's what we calculated in the box there, the SX. And then we get our slope. Yes.
0.519.
0.519. Looks good. That's part of our equation. We need 2 numbers to get our regression model. 2 numbers, that's 1 of 2. The next one is our intercept. And by the way, that's the slope coefficient. And then the intercept coefficient. or I guess you would just call it the intercept estimate. It's just B naught is going to be just the average of the y's, subtract the slope value, multiplied by the average of the x's. So the average time spent, actually, it's the average sales, subtract the slope times the average time spent. We can do that too. So why, we already calculated that, that was $107.40. Subtract 0.519. And we want to put in 62. There. That was the average for the y's. And the x's, I mean, the x's. And we get, drum roll.
74.822.
All right, I get a little bit different. No, 7.4. We're close though. So 107.4 subtract 0.519 times 62. 70, I get 75.222. You want to double check that? Everyone double check, 75.222. And we have our two numbers. Once you have those two numbers, you have your equation. It's this. Which is going to be equal to, now I'm going to put it all together, y hat equals 75.222 plus 0.519 times x. It's always good to write down what the equation is. Notice how I wrote that down first, and then I put it, because it just shows that I know that I'm putting in B naught and B1, because those are our estimates for our true slope and intercept. Why do we want this line? We want to plug in some values of x. We want to know what the next customer, let's suppose a customer spends 40. Do we have any customers that spent, let's take a look at it. So we don't have 60. So we could, this is what the line's for. We don't have 60 minutes. So what would be the average amount of money a customer who spends 60 minutes, what do you think they're going to spend? So you can just sub in 60 and you go, okay, 75.222 plus 0.519 times 60. You can go, oh, they're going to spend roughly $106.36. Now, a way to know if you've done this correctly is sub in X bar. That's the average time spent, 62. And you'll see when you do that, what do you think should be the output? What should be y hat equal to? I'm going to put 62, that's X bar. What should be the output? What do you think? I put in the average X, which is 62 minutes. This is a way to know if you've done all your calculations correctly. It is. You should get 107.2, which equals y. So y hat becomes y bar, and it's one of our regression rules. If you sub in the average X bar and you get the average y, you've done everything correctly. All good. That means all those sums of squares were done perfect. And this is good. So sub in XY, output is y bar. So average y gives you y bar. And you can see this, we can even put that on. So 62 minutes would be about here, and $107 would be about here. We usually do this, X bar, Y bar, that's the pair. And it usually is, it's right on the line. It will be right on the line. So I could probably estimate the line by plugging in some more values for X and getting it, but I'll just sort of draw what it would be. It would be, I'm not going to be able to do it. It's going to be something like that. But that value, that Y bar and Y. X bar and Y bar, the least squares regression line runs right through it. That value, 62 and 107.2. 107.4, sorry. It should be 0.4, right? 40 cents, we said? 40 cents, yeah. It does work out to be that. 107.4, and it should be right on that line. Right? Any questions on that? That's. We're gonna do lots of examples like this. If you're able to get those three sums of squares, or if they're given to you, you should be able to easily spin out your two numbers. You need two numbers, the slope and the intercept, and you have your equation. And now we can just literally put in values for the x. We can also get the correlation coefficient, which should be conveniently on the next slide. You'd almost think I planned this. So there's R. Can we get R? Now, we said it's going to be a positive number. It looks like a very positive. Would you say it's close to 1 or medium or weak? What would you say, just looking at those 5 points? Is the correlation coefficient R going to be moderate, strong? We usually say strong or weak.
It will be strong, right?
Strong. So you're predicting it's going to be close to 1, right? Let's see what it is. Let's put in our values. So R equals the sum of the xy's in the numerator, divide by the square root of the sum of the x's, multiplied by the sum of the squares for the y's. We can get all that in. So the sum of the squares of the xy pairs we calculated to be, I'll just scroll back up. We got that as 2326. So that's our numerator. 2326 divided by the square root of the x's is the first value. We got 4,480. So we'll plug that in. And we're going to multiply, make sure it stays in. Keep your values inside that square root. We're going to multiply it by the y's, 1265.2. And we should get a number close to 1, we said, right? Will this all boil down to a number close to 1? Let's see. It looks like it's hard to believe it will, but let's see. 2326. Did anything go in here incorrectly? It looks okay to me. 4480. Wow. Okay, let's round to 3 decimals. Anybody have it? Believe it or not, what does it boil down to?
5.977.
Yeah. 0.977, remarkable. You can't get closer to 1 without trying. So all that ratio boils down to a correlation coefficient R. You remember what that is from econometrics, right? That's the same R that we learned there. Correlation coefficient. And it's going to be 0.977. And so our R is equal to 0.977. And we have what is called R squared. R squared is when we take R and we square it. It's a way, and it's literally called the coefficient of determination, but in when we do collaboration on these regressions, we just call it R squared. And R squared is a way to assess the fit. And so if you think about R, if we're squaring a value, it's going to always be positive, right? When you square any value, it's positive. So it's going to be 0.977 squared. And it's going to be equal to 0.955, or we usually express it as a percentage. And the closer to 100%, the better the fit. So this is remarkable. We have a 95.5% R squared.